Hello everyone, this video is a demo video based on the lecture today on reverse engineering and PWN. So what we're going to do today is a demonstration on reverse engineering buffer overflow vulnerability, more precisely a red to win that you might see very often in CTF challenges. So red to win means that we're going to try to divert the execution flaw and try to hit a function, a win function that might spawn a shell in most cases. Let's get straight into it. So here we're gonna firstly navigate to our folder. So what we have here is the directory ELF32 with the compiled binary. We're dealing with 32-bit binaries, 4-byte addresses. A solver script that we'll see at the end, and the file that we're going to be interested in, the C code. So we're going to treat this exercise as if we didn't know the source code, so in a black box way. But for the sake of understanding, we're going to check it out first. So what we can see here is exactly the permissions it's been compiled with and the exact compiled command. So first thing that jumps is we don't have ASLR or PIE, so no randomized addresses. We do have non-executable stack that is on, and non-executable heap as well, but that's not going to be a problem here. No source verification, no stack smashing, so no canaries. Okay. And we are in 32-bit. When we look at the code, we see firstly we see our win function straight away, so that's where we're going to try to jump execution flaw to. That's going to spawn a shell. We got a random function here, and main or entry point. So that's defines a variable, defines our welcome function here, and calls it here, and our variable here. So a buffer of 128 characters, but just under we get user input for up to 133 characters. That's exactly where our buffer overflow is going to happen, stack buffer overflow per se. So let's treat it as if we didn't know that. Firstly, I would open up Ghidra, and let's make a new project, and let's check out what we're dealing with. Right now. So new project, non-trade project, name it to win, and I'm gonna open it up. Perfect. So I see straight away it identified it at 32 bits, so and in ELF formats, which is nice. Let me analyze it. Okay, and now we can start checking it out. So what we have in our functions is we always start on main, check it out first, and what do we have here as an entry point? We identify our first variable of 128, then we see our navigets here taking 133, so that's exactly our overflow, and we do call the function that is welcome, and that does absolutely nothing. We also see there is a function called spawn shell, which does spawn a shell, so that's going to be very useful, and that's where we see we're going to hijack our execution flow. So now that we see that, let's go in the PWN. So I'm gonna start up PWN on my binary on one side, then on another side, something I should have done first is I'm gonna check out my binary, and I see it's so an ELF, so in a Linux format executable, a 32-bit as we said, and something that's going to be very important for the following exploits, least significant bits first, so Little Endian format, meaning that we'll have to reverse the addresses. So I'm gonna open up another window and check something out. If we didn't have Gedra and you know how to read assembler very well, you could always do something like that. Using objdump and very nice arguments, you get a colorful output, and you can see exactly the spawn shell function that's gonna be where we want to be. The welcome function that doesn't do anything, and the main function where we get our fgets right here, taking our user inputs, so that's where we want to jump. One thing we do see with objdump right now is spawn shell address. Spawn shell address is right here, so that's very nice. That's the address of the first instruction of the spawn shell function. That's where we're gonna want to jump, so that's one thing that we have. Because we are in little endian least significant bit first, we're gonna have the address is gonna be like this: 86 91 49 sorry 86 91 04 08. So that's gonna be the format of the address. But let's not go too quick, and let's first check things out. So in GDB, we're checking things out. We see we have exactly what we're expecting. So let's put a breakpoint at main, and maybe put a breakpoint at main plus 63, if we want to be exact. Not too much, but not too close. So let's do that. Okay, let's run it and see what happens. Okay, so what we want to be in, what we're going to be interested in is this output here for now. Just under we see the actual content of the stack, and if we go above here we see the contents of the registers. So let's continue. I want to go next instructions. I don't want to start jumping. Okay, I continue. I'm at the beginning of main, so I'm just walking in main right now, and I'm gonna hit my fgets. Hitting my fgets right now. So now I'm gonna have to give user inputs. Here I'm trying to see if I can cause a segmentation fault, so overflow. I know the buffer is 128, so I'm gonna have to put a lot of A's, and I'm gonna see if I can trigger something. Hopefully that's enough A's. You're never too sure. Okay, invalid address. That's A in hexadecimal, so I can see as well that my registers are full of A's. So that's perfect. I caused the 6-7 a segmentation fault. Exactly what I'm looking for. So this is confirmed vulnerable. Now what I want to do, and what I'm gonna do, because I have POMDBG installed, is I'm gonna use cyclic to generate a cyclic list. And this is again the case I didn't know that I had a list of 128 characters, a buffer of 128 characters, but I'm just going to check out the offset in a full demonstration measure. So right here I'm gonna run it again. Once I want to make sure I have this copied. I'm gonna run it again. Then I'm gonna go a bit quicker this time. Then I'm feeding some inputs. Then I get this. So the return address is exactly that, and it's an invalid address. That's exactly what we want to put in cyclic. And it's going to tell us where in the cyclic list the offset could be found. So this offset is 128. It matches exactly as what we know from the beginning, but it's a very useful thing to know to find offsets. So now that we know all this, we can work on our payload, and I like to use Python 2 so I don't have to use the B to specify stuff. Print, I'm gonna print, so 8 characters, for the length of the buffer plus the return address, and we said the return address was, sorry, not the return, just the win address is 86.91.04.08. 80, so in 5.8, 86.91.04.08. And I'm gonna put that in a file that I'm gonna call payload. Perfect. So now I do have my payload. What happens if I check my breakpoints? I want to delete all my breakpoints. Perfect. I want to break at spawn shell, and I want to break at main. Actually, I don't even want to break at main. I just want to see if I can break at spawn shell. So now I'm gonna run it, and I'm gonna feed it my payload, and I'm gonna see if I can break at spawn shell. If I do break at spawn shell, that will mean that my payload is good and that I managed to return to that function. If I don't, my return function failed. And it seemed that we managed to do this. So this means that we are now in spawn shell, so we do manage to spawn shell. So now that we know it works, what do we want to do? We're probably going to exit on DBG, because that's not our next steps. We have our payload that's perfectly ready. We want to do that. So you're going to tell me, okay, just use your payload and redirect it to the binary. Yes, that could work, but that's not gonna work, because if you remember correctly, here we spawn a shell, but to spawn a shell you need a standard input to be open, and you need a way to interact with TTY. So to do that, you need to chain a cat command, and this cat command is going to be cat payload. So normally you would do something like that, and you would see that you don't get anything. So if you do want something though, you would do something like that, because the second cat minus is gonna block the standard in open, and this is gonna feed everything to the program, and it's gonna keep it hanging, and you can see that it opens something. And if I type ls, oh, this is a terminal, and if I type LSNA, I get everything that I want. Who am I? I am exactly the user that I wanted. But imagine if a root user did that and set SUID privileges, it could be very, very dangerous. So here Enigma does not have automatic root, but you could try to do something. So this gave me shell access, and you do need to really keep in mind this last part where you have to keep the standard in open when you want to spawn a shell. So when you want to read a flag, it's okay, you can just change your payload, your buffer overflow, and read your flag. But when it's a shell, you might need to do that. One thing that does happen is if you use spawn tools in Python and you do that, you can automatically keep it open by using this p interactive. So if you use spawn tool in Python, you'll see the solver script is incredibly easy. You just import spawn tools and you set up your process by saying what you're going to use. So I used it from a directory below that, so that's why there's this. You set up your payload, and actually we're going to do it right now. So let's check it out. So this was another address before. What was our address? 86910408. So 86910408. Then I just send this payload to my binary and I keep it interactive. That was a line for explaining the other. There's another way of doing it. You can directly chain it instead of putting it in a file. So with this being done, I'm gonna save it and I'm gonna run it. Oh, I don't think I have font tools installed here. Okay, now that this is done, we can just execute this. What happened? Oh, because I'm in solver. Sorry. Now if I do now it runs and it exploits. It run the local process, it sent exactly my payload, and it got a shell. With that I can switch it to interactive mode and you can see this shell works. This shell does give me access to everything that I have and that I had before, so it works well. It even has color. It might be more stable than the shell you just get normally, so you do encourage everyone to use that. This is the end of this demonstration on reverse engineering and PWN. If you're interested, there are higher difficulty challenges. You can tackle rope chains, and you can check them out on RootMe. You can check them out on Hack the Box as well.